Imagine a machine that can write a sonnet, debug complex software, and draft a legally binding contract, all within the span of a few seconds. For decades, artificial intelligence struggled to string together a coherent paragraph, let alone mimic the nuanced fluency of human thought. Then, seemingly overnight, the digital world was flooded with systems capable of holding dynamic, context-aware conversations. This sudden leap from clunky chatbots to hyper-articulate digital assistants was not the result of a million small improvements. It was triggered by a singular, profound shift in how computers process information, a conceptual earthquake that permanently altered the trajectory of modern technology. To understand this revolution, one must look at the landscape of artificial intelligence before the turning point. For years, the dominant approach to processing text was built on recurrent neural networks. These older systems read data sequentially, moving word by word, strictly from left to right. If you fed a recurrent neural network a long paragraph, it had to process the first word, hold on to its meaning, move to the second word, and so on. It was a tedious linear march through data that mimicked how a human might read a book, but it created a massive bottleneck in computational efficiency. The fatal flaw of these sequential systems was a severe case of computational amnesia. By the time an older model reached the end of a long sentence, it had often forgotten the context of the words at the beginning. If a paragraph started by mentioning a blue car, and 3 sentences later referred to the vehicle, the model would struggle to connect the two concepts. This inability to maintain long-range context is exactly why early digital assistants felt so robotic, frequently losing the thread of a conversation after just 1 or 2 exchanges. The paradigm shattered entirely with the publication of a landmark 2017 paper by researchers at Google Brain. The document was titled, "Attention is All You Need," and it introduced a radically different framework called the transformer architecture. Instead of trying to fix the memory issues of sequential reading, the researchers proposed abandoning the linear approach altogether. They envisioned a mathematical structure that could look at an entire sequence of words simultaneously, completely bypassing the bottleneck that had held artificial intelligence back for years. At the heart of this new architecture was a novel mechanism known simply as attention. In this context, attention is a mathematical operation that allows a model to weigh the importance of every single word in a sentence against every other word, regardless of their physical distance from one another. It calculates relationships and dependencies in parallel, instantly mapping out a complex web of context. When the system processes a sentence, it does not read from left to right. It processes the entire block of text at once, understanding how each piece modifies the whole. Consider the word bank in a sentence. If the sentence discusses sitting by the bank of a river, the attention mechanism immediately detects the strong contextual relationship with the word river. If the sentence discusses depositing a check at the bank, the mechanism links the word to financial terms nearby. The system simultaneously scores these relationships across thousands of words, creating a highly accurate, multi-dimensional map of meaning. This parallel processing capability was the master key that unlocked the true potential of machine learning. Because the transformer architecture processed data in parallel, it could take full advantage of modern graphical processing units, the specialized hardware originally designed for rendering video games. Suddenly, engineers were no longer constrained by the slow, sequential training times of the past. They could feed unprecedented volumes of text into these systems, training them on massive swaths of the internet in a fraction of the time it would have taken older models. This scalability birthed a new era of artificial intelligence, characterized by sheer, brute force computational power. This scaling gave rise to the large language model, or LLM, a type of artificial intelligence trained on vast amounts of text data to understand and generate human language. The transition from small, specialized algorithms to massive, general-purpose LLMs triggered an arms race across the technology sector. Companies realized that with the new architecture, performance scaled predictably with the amount of data and computing power thrown at it. The more text the system absorbed, the more sophisticated its understanding of syntax, grammar, and reasoning became. The economic implications of this architectural shift were immediate and staggering. Tech giants began investing billions of dollars into massive server farms, stockpiling graphical processing units as if they were precious metals. The infrastructure required to train these massive models became a new kind of industrial capital. Data centers consuming the power of small cities were erected specifically to run the complex matrix multiplications required by the attention mechanism. The architecture had not just changed software, it had fundamentally reshaped the physical infrastructure of the global technology industry. The theoretical power of this framework became a tangible reality for the public with the release of ChatGPT. This application served as a highly polished, user-friendly interface for a massive LLM built entirely on the 2017 breakthrough. Within days of its launch, millions of people were interacting with an artificial intelligence that could debate philosophy, write complex code, and draft marketing copy with eerie fluency. It was a watershed moment, proving that the underlying mathematical theories had successfully translated into a product that could augment human cognition on a global scale. The sudden availability of such capable systems sent shockwaves through the global economy. Industries heavily reliant on text generation, from customer service and legal drafting to journalism and software engineering, faced an immediate reckoning. Professionals discovered that tasks which previously required hours of human labor could be executed in seconds by a well-prompted machine. This was no longer a theoretical research project confined to a laboratory. It was an active, disruptive force, fundamentally altering the value of human intellectual labor. Yet, as the deployment of these massive systems accelerated, profound ethical dilemmas emerged from the shadows of innovation. Because the architecture requires staggering amounts of data to function effectively, developers scraped the internet, absorbing copyrighted books, private articles, and personal blogs without explicit consent. Authors and artists began to realize their life's work had been ingested to train commercial products. The debate over intellectual property rights and fair use in the age of generative algorithms became one of the most contentious legal battles of the modern era. Beyond the origins of the data, the outputs of the models themselves presented a critical challenge. The architecture is fundamentally a probabilistic engine, designed to predict the most likely next word in a sequence based on its training. It does not possess a true understanding of truth or falsehood. Consequently, these systems frequently generate highly convincing but entirely fabricated information, a phenomenon researchers refer to as hallucinations. When deployed in high-stakes environments like medical diagnosis or legal research, these confident fabrications pose severe risks to public safety. To mitigate these risks, researchers developed a technique called reinforcement learning from human feedback. This process involves human operators grading the model's responses, essentially teaching the system to prefer helpful, accurate, and harmless outputs. While this alignment process significantly smoothed out the rough edges of early models, it introduced its own set of philosophical questions. By relying on human graders, developers were inevitably embedding specific cultural biases and subjective moral frameworks into systems that were being utilized by a diverse global population. Despite these ongoing challenges, the underlying mathematical principles proved too powerful to remain confined to text. Researchers soon discovered that the exact same attention mechanism could be applied to entirely different types of data. By treating patches of an image or segments of an audio file as a sequence of tokens, similar to words in a sentence, the architecture began conquering the fields of computer vision and speech recognition. The framework was rapidly evolving from a linguistic tool into a universal processor of human information. The most profound application of this universal processor occurred in the realm of molecular biology. DeepMind utilized the architecture to create AlphaFold, a system that solved the 50-year-old grand challenge of protein folding. By treating the sequence of amino acids in a protein like a sentence in a foreign language, the attention mechanism successfully predicted the three-dimensional structures of nearly all known proteins. This breakthrough dramatically accelerated pharmaceutical research, demonstrating that the technology could decode the fundamental building blocks of life itself. As the architecture permeated scientific disciplines, it shifted the very nature of human discovery. Climatologists began using it to model complex weather systems, while astrophysicists deployed it to analyze vast data sets from space telescopes, searching for anomalies that human eyes would miss. The technology was no longer just mimicking human language. It was identifying hidden patterns in the natural world, acting as an intellectual force multiplier that allowed researchers to tackle problems previously deemed too complex for traditional computational methods. However, the relentless march of progress is currently colliding with physical and logistical realities. The strategy of simply feeding more data into larger models is approaching a hard limit. As researchers estimate, we will soon exhaust the supply of high-quality, human-generated text on the internet. To sustain the pace of improvement, laboratories are experimenting with synthetic data, training new models on the outputs generated by older models. This creates a precarious feedback loop, raising concerns about degrading quality and the amplification of latent errors over successive generations. In response to the unsustainable energy demands and data limits of massive server farms, a new frontier is opening in the pursuit of efficiency. Engineers are fiercely competing to compress these powerful architectures into smaller, highly optimized packages that can run locally on smartphones and personal computers. This shift toward localized processing promises to enhance user privacy, reduce latency, and democratize access to advanced computational tools, ensuring that the power of parallel processing is not exclusively controlled by a handful of massive technology conglomerates. As the models become more sophisticated, the debate surrounding artificial general intelligence grows increasingly intense. Some experts argue that scaling the current architecture will eventually lead to systems that match or exceed human cognitive abilities across all domains. Others maintain that while the attention mechanism is a brilliant tool for pattern recognition, it fundamentally lacks true reasoning, causal understanding, and consciousness. They suggest that achieving true general intelligence will require an entirely new theoretical breakthrough, just as profound as the one that occurred in 2017. Regardless of what the future holds, the legacy of that single Google Brain paper is permanently etched into the history of human innovation. By teaching machines how to pay attention, researchers unlocked a level of computational fluency that redefined the boundaries of what technology can achieve. The transformer architecture did not just revolutionize modern artificial intelligence, it rewired our relationship with knowledge, communication, and discovery, serving as the foundational engine for a new era of human capability.